Welcome to Lesson 1's suggested problem for PH 205. This is text problem 42-14. It is a suggested problem for Lesson 1. If this is your first time watching one of these videos, the way I do this is I go through the problem modeling the solution. I'm going to use the physics problem solving format as I go. But the one thing I ask is that you follow along with a blank printout of the problem from SharePoint or a blank scratch piece of paper. I will periodically stop during my recording and ask you to work ahead a few steps. And then once you are ready, you can resume the video and catch up with me and see how you did. Okay, so there is going to be some two-way interaction here as I work through a little bit, you work through some, and check. All right, well, let's go ahead and get started. First up is our read step. This is a very careful reading of the problem. We want to be able to identify the type of problem that we are faced with and any embedded indicators that might help us figure out what equations to use and guide us down the right path towards the solution when we actually get to the solve step itself. So from this problem, I'm asked to find the binding energy per nucleon, and I'm giving americium. And I'm also given some information about the masses of neutrons, and here it says the mass of hydrogen 1, which is essentially just a proton and an electron. Now the mass of the electron is 4 orders of magnitude smaller than the mass of the proton. So essentially what we have here is just the mass of a proton. So as we go forward and calculate the binding energy, this is going to be the mass of our neutron, this is going to be the mass of our proton, and see how that compares to the total mass of our americium atom itself. Okay, so we've done our careful reading, we figured out, hey, I've got a binding energy problem. The key is that it's per nucleon, and so we'll get to that in a moment when we get through to the solve step. So I'm going to write down a couple words that kind of help focus this problem. All right, next up we have the given step. This is where we write down all of our given information. It just so happens that everything we need for this problem is actually given there right for us. The one thing that we don't have is the number of neutrons and the number of protons. And it's actually given right here. So we can do some quick algebra to figure out how many neutrons we have and how many protons we have. The number of protons is really easy given the form of the information they have in the problem. Americium 244 has 244 nucleons. That's protons and neutrons. The nice thing is that the lower number in that form, this 95 right there, represents the number of protons in there. So the number of protons is 95. So the number of neutrons is 244 minus 95 equals 144 neutrons. So now that we have the total number of individual nucleons in our americium atom, we can continue on. All right, so our next step is our assumption step. For this problem, we don't have any assumptions to make. We have our atom, we have the number of nucleons. The only assumption we might say is that the mass of hydrogen is essentially the mass of a single proton, because the mass of the electron is really only affecting the number way out here. So we can write that down as our assumption. So I have the mass of hydrogen 1 is essentially just the mass of the proton. All right, let's keep moving. Our next step is the task step. We are tasked with calculating the change in binding energy per nucleon. All right, next step. All right, next up is our physics step. This is where we take what we learned from our read step and what we know we need to do from our task step and actually put down an equation that marries those two together. So this is where you take a look at your physics reference card. So pull out your bright orange or whatever color it is and take a look at your equations. Now we're in the nuclear physics block. Our read step told us we need to look for something binding energy. In our task step, we have delta big E, so BE, that is the change in binding energy. So as I look at our PRC, we do in fact have an equation that gets us that quantity. Now I've spotted it. I want you to pause the video and I want you to write down the equation you think you will need to solve this problem. Alright, so I'll see you in a minute. So here's the equation we need. Hopefully you have the same equation. Now the question is, do we actually understand what all these variables mean? So let's go through them. First we have this first chunk. It is the sum of the mass energy of all the nucleons present in the americium. So as we look back at our given step, we know that we have 95 protons and we have 144 neutrons. And so the mass energy of those nucleons is going to form this first chunk of mass energy. We then subtract from that quantity the total mass energy of americium in its fully compressed form, i.e. The actual atom itself and not the individual nucleons. And we will find that the answer is not 0. Okay, so let's get into the solve step. We now have our equation. Now we need to actually put some of our given information, we make our assumptions, and actually solve the problem. So we have our equation that we have from our physics step. Now when we actually go to put it together, first off we notice that each of our terms share one variable in common, and that's the speed of light squared. I can use the distributive property and put it on the outside of our brackets here. And on the inside, I can still look at the total mass of my individual nucleons subtracted from the mass of americium itself. So I have my 144 neutrons and I have my 95 protons, and I subtract from that the mass of americium. And I multiply that times c squared. Now notice that the mass we're using is in atomic mass units, or U. We will take care of that conversion with our c squared. And on the back of your PRC, there is a conversion for that, and our change in binding energy will result in an energy in mega electron volts. So do not be frightened of this strange mass unit. It will all work out in the end, I promise. Now, this only gets us the binding energy. It doesn't get us to calculate the binding energy per nucleon. So to get the binding energy per nucleon, we have to figure out, well, how many nucleons are there? Well, it's back in our given information. Americium 244. There are 244 nucleons in that atom. So we're going to take our binding energy value and divide it by the total number of nucleons, 244. I just realized that I did some very poor math. 244 minus 95 is not 144, it is 149. So I apologize, let me fix that real quick. Now I've made my corrections. I've written out the binding energy per the number of nucleons, and so that gives us the binding energy per nucleon, and I have that as the last step right there. Now from this point you can actually put in your given values for the mass of the neutron, the approximate mass of the proton given our mass of hydrogen, and the mass of americium. I also have listed the value for c squared, and that is in per that is in mega electron volts per atomic mass units. Now, I didn't just pull that out of thin air. It is on the back of your PRC under the fundamental constants portion. All right, from this point, you put in your given values and you get a value back. So we get 7.521336, and the solution online has a 0 after that, but let's take a look at our significant figures. So our mass for americium has 9 significant figures, our mass for hydrogen has 7, mass of the neutron has 7, but our constant only has 6. So we need to go with the fewest number of significant figures. It is 6 by way of our speed of light squared. So we have 1, 2, 3, 4, 5, and 6. That is our solution. And you might be wondering, why are we calculating the total binding energy per nucleon? Well, going with the total binding energy per nucleon gives us a feel for how well packed the nucleus is. The tighter packed it is, the harder it is to separate those nucleons into individual particles, or even just separating it into 2 or 3 or 4 daughter particles. And we see that in nuclear decay. And we'll get more into that in later lessons as far as fission goes. But when we look at this total binding energy per nucleon, the lower the value is, the easier it is to separate those nucleons. It's more likely for a decay or fission event to occur. So something like iron that has a very high binding energy per nucleon is not going to decay on its own. It is about as stable as it gets. It is generally what's left in any type of nova or supernova when a star can no longer continue diffusion. All that's left is an iron core, and what other elements have fused into heavier elements that then go off into space and help seed other star systems like perhaps ours. Anyway, completely separate topic. Hope you enjoyed this problem. I will continue to do one suggested problem per lesson as a way of seeing how a problem is done to standard. All right, thanks a lot. See you next time.